this morning through the core network of 5G. This is a topic that does not involve radio links, wireless transmissions, not directly. It focuses on the infrastructure of the network. Okay, so it's a bit different from what we have seen till now. Technically speaking, this class is not so difficult, but there are some innovative concepts like SDN and FFV. I don't know if you have heard of software-defined networking and network function virtualization, that are totally new concepts that have been introduced, and they are the basis for 5G infrastructure, network infrastructure. So the topics are kind of between telecommunications and computer science, as you will see. And there are some also pointers to resources that you can use, you can try if you would like to have an hands-on approach on these topics. So you can download some resources and use them. So there is no lab associated with this lecture, but you can try by yourself at home. There are free resources that you can use. Okay, so let's start. As I said, this is about the network infrastructure. Sorry, it doesn't advance the slides. What should I do? Sorry. Okay, now it works. Okay, thanks. So as I was saying, let's look at the core network of 5G, and this will be our outline. So we'll briefly recall what 5G is, but in particular considering the network infrastructure. And then we will look at the software-defined networking technology and what SDN can do for cellular networks, for today's cellular networks like 4G networks. And then we have network function virtualization, NFV, so we will introduce this concept. And then the combination of the two, SDN and FFV, will be basically the enabling technology for the 5G infrastructure. So then we'll come to 5G, and at the end we also briefly mention this new paradigm that is multi-access edge computing, MAC for short, that is also sometimes called, because the concept is very similar, fog computing. So that's why I was saying that we are touching also some aspects that are closer to computer science than to telecommunications. Okay, so let's start with the first aspect, that is what is 5G from the point of view of the core network. Now, we know that 5G evolves, and it relies on LTE Advanced, and combines many, many aspects. So it's quite complex technology overall. For example, you can see here that MAC, multi-access edge computing, that we just mentioned, was present already in LTE. But this concept was not, let's say, developed within LTE, while it will be very important in 5G. And then we have this concept that is actually totally new and that relates to 5G only, that is the need to support vertical services through SDN and FV. Now, this sounds, I guess, very, very obscure, but we will spend the next couple of hours or 3 hours or so to explain exactly this sentence. What does it mean to support vertical services through SDN and FV? Now, let's start by introducing the concept of vertical. We will come back to that later on, but just to have an idea of what we are aiming at. So verticals are those that provide the services, that want to provide the services to the end users, and the end users, of course, it's us. And you can think of a vertical as a car manufacturer that wants to provide services to its own users that at that point will be the vehicles manufactured by this company. Or e-health service, you can think of smart cities, stakeholders. And then, of course, there are mobile broadband services like virtual reality that you would like to provide to your customers. So verticals are may belong to many different domains. Okay, we mentioned e-health, we mentioned car manufacturers, content providers, of course, can be verticals, and so on. Now, these verticals, think, for example, of a car manufacturer. Now, clearly, they want to use the network, the mobile network, to provide services to their users. But they don't want to manage the network, of course. So the verticals are on top of our network, and they want to use the 5G network so that it can support the services they want to provide. Okay, so the important thing is that they are not going to manage the network itself. It is the mobile network operator that has to manage the network so that this is able to support the services that the verticals want to provide. Okay? And also you can see in this picture that we have drones, so you may also think of innovative services where we use drones, and high-speed trains, so mobility is another important requirement that you may have. In general, each service will have certain requirements that in, let's say, 5G terminology are called KPI, Key Performance Indices. So this is actually an acronym that has become very, very popular, especially in Europe, but also all over the world. And it means performance metrics that you target, that you want to satisfy, target values that you want to meet. And here is an example for natural disaster, public safety, automotive, and also for virtual reality. These are just samples that have been taken from the 5G documentation. So, for example, for a natural disaster application that you should have during a flooding or an earthquake, while the data rate required is not very high, as you can see, latency is not that critical, but you have to support also fast users, and then you want quite high availability and reliability. Availability means the service should be available for this percentage of basically geographical area and also in time. Reliability means instead the percentage of packets, data packets that are successfully delivered to the destination. Connection density is another very important KPI. That is the number of user connections that you can support simultaneously. And basically this use case has got quite high connection density that is required. If we look at public safety, you can see that the data rate is different. Now we have also requirement in terms of latency, and then mobility that is also very high, so it includes fast trains, and then very, very high availability, reliability, while instead connection density is not critical. Automotive, you can see here that you could also have megabits per second. Latency is extremely strict. This is very hard to achieve. High mobility, high availability, reliability, and quite high connection density. And finally, virtual reality. Well, as you can imagine, in this case, the data rate that is required is definitely high. Latency also must be lower than 20 milliseconds, preferably 15 milliseconds, and then others are not that critical. So if we look at this table, what can we understand? What do we say? Well, that each service has got different requirements. So a KPI, a performance metric that is very important for one service is not critical for others, right? So we have a network. Well, we'll have a network that is the 5G network, and our network has to satisfy to support all these services, and therefore to satisfy all these requirements. So that would be practically impossible if you consider the whole network and to configure the whole network so that you are able to provide basically all these KPIs with the values that are required, okay? Because the resources are limited. So what is the solution? What is the concept that they have introduced that is really the key point to be able to do that? Well, that's what is called network slicing. So network slicing means that you've got your network resources, and actually it extends also to the radio link. Okay, it's not just for the infrastructure, it's for all type of resources. What you can do is to slice your system, and each slice will be assigned to a different service. So it's like a bread loaf. You slice it, and then you basically configure each slice of resources in such a way that on that slice you are able to, for example, provide natural disasters. So the slice will be created and configured so that you meet these requirements. Not this, but the natural disaster one. And then you take another slice and you assign it to public safety. And at that point, you configure that slice to meet these requirements, not the others. Okay? Then it becomes feasible, right? Because you have a certain amount of resources, you focus on that, and basically you configure those resources for that specific service. So the idea is great, and it's going to work, but the problem now is how can we slice our network resources, right? It's not easy. It's not actually a bread loaf, as we said. So how can we do that? And here are the technologies that we mentioned before. So software-defined networking, SDN, and network function virtualization, NFV. The combination of the two will give us the possibility to achieve and realize this concept of network slicing, okay? So now we have clearly to look at SDN. We need to understand what NFV is and how they can be combined for this goal. So our next point will be indeed SDN, software-defined networking, okay? So SDN is, we'll say, the first key technology to realize the concept of network slicing, okay? Let's start with this slide, where basically we have a comic that says that everything nowadays is SDN. And indeed, if you look at the scientific literature, but also technical magazines, it's very likely that you will find this acronym SDN. And here we have a short list of sentences that basically summarize what SDN is and what it does. Now, we can read it through. Of course, I expect that you will not get you will not understand these sentences, but what we will do next will be to explain actually these concepts. So here you have a brief summary, and afterwards you can come back to this slide, reread these sentences, and see if they have a meaning, okay, for you. So first thing is the decoupling between control plane and data plane. So this is what SDN does. This is the most important thing that SDN does. It decouples the data plane from the control plane. And as a consequence, we now have a control plane that is centralized, logically centralized. Now, this controller will be able actually to program the network. And then what we will have in the end is the possibility to have an abstract view of the resources of the system. Not just networking, but also computing and storage resources. So don't be scared. It's fine if you didn't understand anything. Just keep in mind this slide for later when you are home and you review the slides. So we'll start from the basics. That is what we have, let's say, today, the traditional computer networks. Okay, let's just recall what they are and how they are made. So let's consider, first of all, the data plane. That means basically how our network nodes deal with data packets. So this is an example of a small network that is composed of switches. You may have routers, of course, also. But let's consider switches for now. And from the point of view of data plane, so looking at the data packets, what do? Well, they basically forward the data packets, right? So switches will just forward the packet from one switch to the other. And hopefully they will reach the intended destination starting from the source that generated the packets. So our networks now have got these switches whose goal is to forward packets. They also do some filtering, buffering, marking, but the main goal is packet forwarding. They are very fast. The functions are implemented in hardware, so the time scale of our data plane is the packet scale, so very, very fast. Then we have on the switches themselves also a control plane. That means each switch implements some algorithms, right, that actually may be algorithms devoted to traffic forwarding, so they tells you where to forward a packet, to topology discovery, and in this case the control plane that is basically distributed, because these algorithms are distributed, they reside at each switch and each switch will make decisions. Well, in this case the time scale is is slower than before. So this is the flow time scale, okay, the traffic flow time scale. And then finally we have the management plane. Well, management means to monitor the network, to monitor the traffic, and in this case we have a human time scale, so very slow compared to the previous ones. So this is what we have today, and in a nutshell, if we want to summarize the main concepts of our traditional computer networks, is that, again, they focus on packet forwarding, and then, as we saw in the picture, we have that every switch has got a data plane, a control plane, and actually a management plane, and these devices are closed devices, right? You buy a switch or a router from a vendor, and you cannot put your hands in the switch or the router. You cannot modify anything. It's a closed environment, okay? Now, this is to summarize what we said. So in a very schematic way, this is what we have on a switch. The data plane that, as we said, is implemented in hardware. It's very, very fast. And then we have the control and management plane. So we have an operating system on the switch, on top of which we have the applications. And the applications, as we said, are the algorithms that determine the switching, routing, topology discovery, and so on. So since each of these objects is closed, it implements proprietary solutions, how can we guarantee interoperability between the different pieces of equipment? Well, we have interoperability thanks to the protocols. So the protocols that these switches use to communicate are standard protocols. So even if you have closed equipments, you don't know exactly what is in there, but the protocol is standard so that you can let the switches communicate whatever the vendor is. So let's look at the protocols. So the protocols that have been proposed and adopted. Well, here, unfortunately, the fonts are a bit small, but what you have here is the number of standard protocols. So it reads number of RFC. RFC means request for comment and is what you call within the IETF, the Internet Standardization Forum. So you use the request for comment to denote the documents issued by this institute, and they are basically standards. And here you have the years till 2014. So what this tells you is that you have lots of protocols that have been proposed, and the number has increased significantly very, very recently. So this means that the world that we are looking at is extremely complex, right? And it's becoming more and more complex. Here is another plot that actually highlights the origin of each proposed protocol. So here we have, again, basically the number, and here is the name of the company or institution that proposed the protocols. So the meaning of this plot is that most of the protocols have been originated by the vendors. There are very few, for example, universities. There is MIT, there is UCLA, there is Berkeley, but all others, most of them are companies. So again, this tells us that this world is actually owned by the vendors, by the companies. So is this good? Well, of course, since the equipments are closed and we cannot put our hands on these products, well, probably we don't like it very much, right? Because we are researchers, we are scientists, we would like to experiment with things and modify things and see if we can improve them. But in general, we have that the whole system, think of a mobile operator, well, it would be very difficult to manage and very costly, right? Because you have, as we said, closed equipments, so you cannot do anything by your own. You rely on the vendor, and whenever there is a change, you have to change the whole equipment, and for the mobile network operator, that's a very costly solution, especially nowadays that things evolve so rapidly. So this is why they have basically supported, the mobile network operators have supported this new paradigm that is software-defined networking. Software-defined networking tries to change what we have, the traditional computer networks, and introduces several novelties. So first of all, what it does, as we said at the very beginning, was to separate, decouple the control plane from the data plane. So while before we had the switches that had both now our switches will have only the data plane. The control plane will be somewhere else. So this means that we have a controller, that is our control plane, that is out of the switches, and as we said, conceptually is centralized. Okay? So this is very important. So now we have decentralized control plane that may reside anywhere, even on general purpose hardware. And this is very important because now, well, you have some software that can run on any hardware. So you can understand that the cost of it will be much less, right? And since we have one controller that is logically centralized, so physically you may have several controllers, but the idea is to have one controller. That controller will have a global view of your network. So this means that it will be able to make very good decisions, possibly optimal decisions, because it has got the all information related to the whole network. So our controller, that is a sort of network operating system, will be also able to program the network. So it will be able to tell the switches what to do. And so the result will be a totally new architecture. And as we will see, we have that our switches, based on the instructions that they receive from the controller, they will be able to perform flow-based switching. And finally, what we'll have is that on top of the controller, that as we said is a sort of network operating system, we may have any kind of applications that you like. You will be able to develop your own application related to routing, load balancing, whatever you like. So now we are going to focus on the main concepts that we have here. First of all, let's look at this graphical representation of the traditional computer networks that we explained before and what we'll have with software-defined networking. So as we said here, switches have got both data plane, control plane. This is the new concept where the switches, as we said, now have only the data plane, and the control plane is somewhere else. It's logically centralized, so we have one entity that implements the control plane. Okay, so this is the decoupling between data and control plane that we said before. So now we have our controller, and these are our switches. So based on what we said, since the switches implement the data plane only, well, they will be very fast, because that's hardware. Most of the what is in there is hardware, and they implement the forwarding tables in hardware. So they are very fast, but they are dumb, because all the intelligence is in the controller. As we said, it is the controller that tells the switches what to do, how to forward the data packets of the different traffic flows. So clearly we'll have an interaction between the controller and the switches, right? Because the switch will ask for help, and the controller needs to tell them what to do. So we need a protocol also in this case to realize this interaction. And there are different protocols, but the one that was defined first, and it is the most popular one, is the open flow protocol. Here is the architectural view of our system. So now we have this data plane that is represented by our switches. And these switches interact with the controller. The interface between the data plane, so the switches, the physical devices, and the controller, that is clearly only software, it's a network operating system, is called southbound interface. This interface is an open interface. This is very important because it means that you can develop your own controller and let it act on the physical devices. So provided that you basically have this southbound interface, you can have your own controller that acts on the switches. So we do not have anymore the need for proprietary solutions. Anyone can develop it. So then we have the controller that, as we said, and this is very important as a concept in order to understand what follows, the controller is indeed a sort of operating system of the network. On top of the controller, you will have the applications that are the algorithms, right? As we said, the load balancing, energy efficiency, routing, forwarding, whatever you like, can be developed on top of the controller. So this is the intelligence of the system that makes actually decisions. These are the controller applications that make decisions, and through this, let's say, network operating system imposes its decisions on the switches. The applications, again, talk with the controller through the northbound interface. That is, again, an open interface, so you can clearly have your own application running on your own controller or on a controller that has been developed by someone else. So let me present you also here an analogy that has been made by Nick McEwen. Nick McEwen, you may know him. He has worked a lot on switching and is the one that has promoted this new concept of software-defined networking. So in the past, basically, we had these mainframes that were closed equipment, right? We had specialized hardware, specialized operating system, specialized applications. Everything was closed, and the innovation was clearly very, very slow. And then we moved to personal computers, where we had basically the hardware that through an open interface can interact with any operating system, and through an open interface we can interact with any application. So this is what happened basically in this world, in the computing world, and what is happening through SDN is exactly the same thing. So we are moving from closed equipments that are our switches or routers, and we'll have a hardware that can support our controller, the control plane, and then through an open interface, our applications, whatever application you want to develop. So clearly, we'll have the same effect. That is a rapid innovation, the possibility to develop services in a much more swift manner and at lower cost. Now, let me go back to the concept that we introduced in the initial slide, that was the flow-based forwarding. So what is this exactly, how it works now in our SDN networks? Well, you know that switches have got tables, forwarding tables, that are implemented in hardware, and basically they tell you how to forward the packets, right? So what we have here is tables where each entry, in principle, can refer to a different traffic flow. So the entry of the table is given by three main fields. The first field is the rule. That is basically the mask that you have to use in order to see if the packet header matches. Okay? So you apply this rule, this mask, on the packet header, and if it matches, then the packet has to be dealt with by that entry of the table. The second field is the action. That basically tells you for that packet, for the packet belonging to that flow, what is the action that the switch has to perform. And the action actually may be very diverse. So it can be forward the packet toward this port, but it can be also drop the packet, or send the packet to the controller, or modify something, and so on. And then the third field is for statistics collection. So you just count the number of packets and the number of bytes that have been processed according to that rule. So the switch is also able to collect these statistics. Here is a graphical representation of what we said. So this will be the generic table entry. And as we said, there are these three fields: rule, action, and statistics. The rule, as we said, is a sort of mask that you need to apply to the packet header in order to understand the flow to which this packet belongs. And then for that flow, you need to apply the action that is reported in the following field. And as we said, then we have statistics. Now, the table entries may also have associated a priority level. Why? Well, because we may have rules that actually apply to the same traffic flow. And if this happens, then you need to disambiguate clearly these rules. So you have to know which rule to apply between the two or three that match the packet header. So you need priorities. So you will apply the one that has got the highest priority. Let me give you an example. If you have an entry that says that all the packets, so the traffic flow destined to Y, need to be forwarded to port number 1, and then there is another rule that says all the packets destined to Y and that were coming from port 5 should be forwarded to port number 2. So at that point, we have that for all the packets that are intended for Y and that come from port number 5, well, both rules will apply, right? Because they are for Y, destined to Y. So which one shall I apply? Well, then I have to look at the priority level of the entry, and as we said, the highest priority will win. So the other important concept that we have now is that depending on the action that we specify in the field of the table entry, our device may be a switch, a router, a firewall, a NAT. It may be many things, many different things, exactly the same physical device. Why? Well, because indeed, if you match through your rule of the table entry the longest destination IP prefix, and then your action is forward the packet toward the link, well, then you have a router. If you instead match the destination MAC address and forward the packet through your action, then you have a switch. And then if you have as a matching the IP address and also the transport layer port number, and then you decide whether to drop the packet or to allow the packet, well, that's a firewall. And then you can implement a NAT by matching again the IP address and the transport layer port, and considering that the action can be rewrite the address and the port. So this means that the same physical device that is programmed by the controller may actually act as a different box, right? As a different piece of equipment in traditional networks. And I can change the functions that this physical device performs just by properly coming up with table entries that do what I like. So again, the cost of this system will be much, much lower than the traditional system, because now exactly the same physical device can play the function of many different devices that we had, closed devices that we had before. So this is extremely important. Now, let me also give you some more examples regarding the controller to switch interaction, so that we can better understand when this interaction in particular occurs. So clearly, since the switch is dumb, does not have any intelligence, it needs to receive instructions for the controller, and as we said, we need a protocol to let the two of them talk. And this protocol, let's consider that is open flow. Okay? So we expect that we have the switch where the table is implemented, the forwarding table is implemented in the flow table, is implemented in the hardware. And then we have a software part where basically we have the OpenFlow client. The OpenFlow server will be at the controller. And what happens is that, let's consider our switch that now, as we said, it's more general because it can act as any kind of box, firewall, and so on. So let's call it forwarding element. So let's assume that the forwarding element receives the first packet of a traffic flow. Now, clearly, the forwarding element does not know what to do with these flow packets, right? It's the first time that it receives one of them. So it will basically match the default rule that says send the packet to the controller. So the forwarding element sends the packet to the controller. The controller, thanks to the applications that are on top of the controller, will decide what to do with this packet and the following packets belonging to that flow, and will send back to the forwarding element the rule to install. So now the switch knows what to do. It will create a new entry in its table that says this is basically the mask, the rule, and this is the action, forward to port number 2. Now, these table entries have got a lifetime, okay? So what we have is that the forwarding element will be able to now deal with these packets, but clearly we have that since the rule has got a lifetime, at a certain point it will expire, and when it expires it has to be removed from the table. So this means that the interaction between our forwarding element and the controller is clearly necessary when we have the first packet of a traffic flow, so whenever this happens, but also if the rule expires and we purge the rule from the table, well then if we have another packet belonging to the same flow, we have to interact with the controller again, okay? Here is another example that shows at larger scale how this interaction works. So let's consider that we have a new traffic flow here. So the packet reaches a switch, and the switch does not know what to do with the packet. So as we said, it will ask the controller. And at this point, the controller, thanks to the applications that are on top, will decide, for example, the path that this traffic flow should follow. So it will actually reply not only to our switch that made the query, but to all switches that are along the path of the traffic flow, installing the corresponding rules. So that from then on, all the packets that arrive will be dealt with by the switch that will forward the packets to the next switch and then to the other switch along the path, because they have already received the rule from the controller. So the point here is that the first switch will need to query the controller, but the controller at this point will install the rules on the switches basically of the path, so that they will not need to interact with the controller at this stage. They just receive the rule, but they don't have to query the controller by themselves. And so we are able to deliver the traffic to the intended destination. So what we have here is a summary of what we said and some other information. So here are our switches. As we said, they interact with the controller through the southbound interface. And what the switches do, well, as we said, they will send a request for help to the controller whenever we have a new traffic flow and we have a new packet that we don't know how to deal with. They also will interact with the controller when there is a change in the topology. So they need to report, for example, link failures to the controller. And then they also will be able to send statistics, traffic statistics. Remember the field of the table entry in which we collect statistics to the controller. And then the controller will have to send something to the switches whenever he wants to install rules. He can also uninstall the rules, and then he can query statistics, of course, and he can send packets, other packets to the switches. So this interaction, let's say, it may happen quite often between switches and controller, and it is indeed one of the weaknesses of software-defined networking. This is the overhead that you have in your system due to this switch controller interaction. Consider that in the previous example where we had the entry of the table that expired at a certain point, well, our switches indeed will have a limited memory, and also the cost should be low, so you cannot have very large memory. So it is understandable that the set of entries that you can keep in your table is limited. And this means that if there are many different traffic flows and you need many table entries, well, you need to purge these entries quite frequently, and at that point the interaction with the controller increases, and therefore the overhead will increase. Okay. So here are some examples for the applications that you can have on top of the controller. They are applications that are called controller applications because they are actually within the SDN, let's say, world. I'm stressing this because, as we will see, when we move to NFV, Network Function Virtualization, we'll have something similar that, however, exists outside the SDN world. So these applications are on top of our controller, seen as a network operating system, and they are within the SDN world. Okay? So these are controller applications. They may, as we said, be whatever you like. Dynamic access control. They can be applications to manage mobility, and this is very important, of course, in our mobile networks. So to manage mobility in an efficient manner, load balancing, traffic engineering, energy efficiency, and so on. So here is an example. we have our network of switches, so the data plane. This is our controller, and what we have here is a host. Well, what we have is that when the host generates a traffic flow, as we know, the first packet of the flow will reach this switch, and the switch clearly needs to interact with the controller. At this point, when the controller receives the packet, what happens is actually that we have an application, a controller application, that has registered with the controller, asking to be informed whenever there is a new traffic flow. Okay, when the first packet of a traffic flow arrives at one of the switches. So this application will be informed. Let's assume that this is an application for dynamic access control. So it will be informed that there is a new traffic flow, and it will then inspect the packet and see what to do with this traffic flow, if it can be admitted or not. And once the application has made its own decision, it will inform the control. It will send a so-called intent to the controller, and the controller will clearly impose the decision on the switch. So in this case, the packet basically goes to the controller that informs the application makes the decisions, and if the decision is actually to allow the traffic, then you may have another application that computes the path for your traffic flow. Okay? And in this case, clearly the packets will be routed toward a certain destination. If instead the dynamic access control application that you have here on top of the controller said, well, deny the access, well, then the switch should have dropped clearly the packets of the traffic flow. So let's have a summary for our SDN part. First of all, architecture, so that we have a clear picture of this technology. As we said, we have the switches that are SDN switches, so they need to implement the OpenFlow protocol, and they represent the data plane. They interact with the controller through this southbound interface that is an open interface. The switches for now are completely dumb, no intelligence in there, at least in this version of SDN that we have seen. Then we have the controller, that is the network operating system. It is basically in the middle, so it will interact with the switches as well as with the applications through this northbound interface. And then we have the applications that are the real brain of the SDN system, because this is where we have the algorithms and we make decisions. So it is important to remember that these applications can be developed by third parties. So we did that. Actually, we developed our own application that was an energy efficient routing application using one of the controllers that are there, that is the ONOS controller, and it was really relatively easy. So anyone can do that. Regarding the packet processing, what we said is that whenever a forwarding element receives a packet, we need first to apply the rule, so the mask on the packet header, and classify the packet as belonging to one traffic flow. And then read the action, the corresponding action that the forwarding element has to take. And as we said, this action can be anything. So this means that our forwarding element now can implement any box that you like, any function, network function that you like. And then, of course, if you have to forward the packet, you can send it to the corresponding port that is specified in the action, if that is the action that you have to do. And for the switch controller interaction, what we said is we need the OpenFlow client at the switch. The OpenFlow server will be at the controller. They can interact. The OpenFlow is one of the existing protocols, so that whenever, for example, there is a new packet belonging to a new traffic flow, the switch can ask the controller what to do. The controller is going to program the switch. So here is indeed the concept of network programmability, because the controller really programs the switch. It will insert the table entry. It will install the table entry in the switch. And in this example, well, what it says is that if you've got packets with IP destination 5, 6, 7, 8, well, then you have to send the packet toward port 1 in order to be delivered. Okay, so if you consider SDN, as we said, and let's say what SDN can do, it can be understood by looking at the whole architecture that we introduced. And here is an example that basically includes everything. We have the data plane, southbound interface, the controller, northbound interface, and application on top. And as an example of application, let's consider the Dijkstra algorithm that clearly is a link state routing algorithm. I guess that you are familiar with Dijkstra, right? But anyway, it's a routing algorithm. So it decides which path clearly a traffic flow has to take. So let's consider that we have the switches here, and in particular, the traffic flow has been, let's say, already routed and goes through S1 and then S2, okay? So this is the current situation. But what happens at a certain point is that the S1 switch detects a link failure with S2. So as we said, switches have to report topology changes to the controller, right? So this is one of those cases. Our switch will have to report through the OpenFlow protocol this change in the topology. So through OpenFlow, it will notify basically the controller, and the controller that keeps, registers that describe the network will update, in particular, the link state information that is storing. So now we know that this link does not work any longer. And what we can consider is that since we have made a change in the link state register, we can consider that this application, the Dijkstra algorithm, previously registered with the controller. So when there is a change in this register, it will be notified, right? So now the Dijkstra algorithm will be able to compute a new path for our traffic flow, because it has got all this information from the controller and is therefore able to compute the new path. So one thing that is important to notice is that, as you can see, the applications that are on top of the SDN controller, they register with the controller to be notified upon changes whenever there is an event that has to be dealt with by the application. And the very important thing that we have here is that the SDN controller provides to this application an abstraction, an abstract view of the data plane, of the physical resources. Because as you can see, the Dijkstra algorithm, the information that it accesses is actually the list of link state information and the network graph. Okay, so that's all it needs. It doesn't need any other detail. That's what it needs. And this information is therefore an abstract view. It's a network graph and a list of links, right? So it's an abstract view of what you have physically in the network. So the SDN controller plays this very important role, that is, virtualize your resources. Virtualize the resources means to provide an abstract view of the resources. Okay, and this is very important because you may remember that at the very beginning, when we had the slide with the comic, the last sentence was resource virtualization. We said also computing, storage, but let's focus on networking now. Well, this is it. This is what the SDN controller creates, an abstraction of the network resources. We don't need to know exactly, the details of the single switches. We just need to look at them as nodes and at the links as edges, and to know the cost of its edge. That's it. That's enough for our routing algorithm. So this is very, very important. So let's go on with our example. At this point, as we said, the algorithm computes the new path. And this means that at this point, it will send its decisions to the controller. As I said, we have this intent that is basically a command for the controller, an instruction that comes from the application to the controller. And then the controller will basically translate this decision that has been made by the application into a table entry. Because what the switches understand is table entries, right? So the controller has to, at this point, just translate the path that has been computed by the application into table entries for the switches. So the controller will do that, and through the OpenFlow protocol, it will install these table entries into the switches, so that now clearly we have the new path through which the packets can flow. Let me just check the time. Okay, we still have some time. So I would propose that we can have a break between SDN and NFV. That are the two main topics. So that will be in a while. 10 minutes and we will be there. So I hope we now understood what SDN is, what it does. If you have any questions, please ask. Any doubt, anything that you want me to repeat, feel free to ask. If everything is clear, what we are going to look at now is, let's say, a recent advancement in the SDN concept that is called stateful data plane. Okay? We are not going into the details, but we'll try to provide the idea and some information on how it can be realized. So let's consider this very simple example that refers to load balancing. And in particular, it's a very simple load balancer that can be represented through this finite state machine. So we have these two states, 0 and 1. Basically, when you are in 0, what you have to do is to forward through the upper port. And at this point, you will move in 1. When you are in 1, you forward through the port below, and you move to 0. So the result will be that you will forward one packet through the upper port and one packet through the port below, right? It's that easy. So remember that according to what we said so far, our switches are completely dumb. They don't have any intelligence at all, right? So this is our switch, and the approach that we described so far. At this point, let's call it stateless approach, because in the switch, indeed, we do not have any notion of the state that we may be related to this load balancer, for example. So when the switch receives a packet, what it needs to do, well, it needs to ask the controller about what to do, because the switch clearly does not implement any intelligence. So it will ask the controller, and the controller, you can see that the controller has got this final state machine, so it knows the state. The current state is 0. So what it will say is, well, forward through the upper port, and it will change its state to 1. And then, of course, if another packet comes, we'll have that, it will have to be dealt similarly, and every packet will have this interaction between the switch and the controller. So as you can understand, this is a lot of overhead, because for every packet we have basically 2 packets here due to the interaction between the forwarding element and the controller. That's a lot. That's a huge overhead. So the idea is basically to get rid of this interaction, continuous interaction with the controller, and move to another concept where we have some intelligence at the switch. If you like, this may seem to be in contradiction with what SDN does and what initially stated, but let's say that is an improvement that they introduced in order to indeed reduce the overhead that you may be. The overhead may be overwhelming, and you don't want that, right? So that's why they introduced this second approach that is called stateful approach. Why? Because now the idea is that you can actually implement this final state machine in the switch. So the idea is that when there are decisions, local decisions, that the switch could take, let the switch take those decisions without interacting with the controller. This holds, of course, only when you have local decisions to make. If instead you have, let's say, global decisions that relate to other forwarding elements, well, then you still have to rely on the controller, clearly. But if there is a situation like this one, where the decision is purely local, well, it doesn't make sense to ask the controller all the time, right? So they said, in these cases, let the switch implement this state machine. And in this case, if you are able to do that, if you are able to basically code the final state machine in the switch, well, then the advantage is very significant, because now we have that the switch has got the state, the current state, so when the packet arrives, it will autonomously decide what to do, that is forward up at the beginning when we are in state 0, then update the state, and the next packet, of course, will be instead sent through the other port. So this is the idea. Now the problem again is, the idea is nice, how can we implement it? Because as we know, the switches that we have now are very simple devices, they just have tables, so what can we do? Well, actually what they did was to try to realize this stateful approach by modifying the protocol, the OpenFlow protocol, and by introducing new solutions that include this possibility to have the stateful approach. And in particular, nice one, because it's still very simple, is OpenState. Okay, so open state is like an evolution of open flow in order to deal with stateful approach. Let me give you an example. So what open state does is still to work with tables, but now we have a new table that is installed in the switch. And this new table is called state table. Okay, so here is our state table. So now the packet processing slightly changes with respect to before. The first step is still the same. So we look at the packet header, we apply a rule, we classify the packet as belonging to a traffic flow. But then now we look up not the flow table, we look up the state table. So based on the packet header that we receive, let's assume that the packet header matches this rule, that is the IP source address is 1, 2, 3, 4. Well, then we look up the table and we find the current state of our finite state machine. This is the current state, stage 3, whatever. Okay? So now we have the current state of the machine for that traffic flow. So what we do is to consider the previous mask plus this additional information, that is the current state. And now we look up this flow table, whose name has changed because it has been extended with respect to the previous flow table, but the meaning is basically the same. So with this information, that is the mask, the rule, the previous rule, plus the current state of the state machine, we basically look for the corresponding table entry, and we find the action to be performed. We have, however, an extra column here. That's why it's an extended flow table, because now besides the action, we also have the next state of the machine, of the state machine. Okay, so we now know what to do with the packet, and we also know how the state machine evolves toward the next state, because it's written here. So what we have to do is to apply the action to the packet, and then take this next state and update the state table. So we go back to the state table and update the state corresponding to that traffic flow. So if you think about it, it's quite simple, right? Because it's considering the previous example, well, the switch will first match the packet header with the rule. Then at this point, through the state table, it will acquire the current state. So now we know the state, we know the traffic flow, then we know the action. So it knows that, because it's written in the second table, we know that it will have to forward up. And in the second table, there is also written what is the next state, that is 1. So we go back to the state table, update the state to 1, so that the next packet that it will arrive, it will be dealt with correctly. So very simple, same structure as before, just deal with tables. You need just more tables than before, but not such a big deal, and the benefit that you obtain is a lot in terms of efficiency of the system. Open state is not the only solution to apply a stateful approach. Let me mention also P4. We are not going into the details of P4 because it's very complicated. So P4 is another solution that implements this stateful approach, based on which some intelligence, this basically final state machine, as we saw before, are moved from the controllers to the switches in order to deal with local situation. Now, what I'm saying is that P4 is more complex because it adopts an approach that is completely different. So no tables, but what we have is a sort of program. So it's a code. It's a code that basically needs to be, let's say, compiled by the controller, and then it will be executed by the switch. So the approach itself is more complex. It still matches the idea of programmable network, because actually you program, the controller makes the program that the switch will execute. But clearly, as you can understand, it is definitely more complex to deal with, okay? Because you have basically a code, and you have to compile the code and execute the code at the switch itself. But P4 is gaining momentum, so if you are interested to these research topics, to understand how the 5G network will evolve in the future, you have to develop application services on 5G. You may want to keep an eye on the evolutions of P4. Okay, so this is a bit, oops, sorry. This is a summary of what we said about the stateful approach implemented through the open state. So just to summarize, we have that the packets come in the forwarding element. You still look at the header of the packets, but then you use the rule to first identify the right entry in the state table. In the state table, you get the current state, and then with all this information, you look up the extended table, where you get the action to perform and also the next state. The next state basically is used to update the state in the state table and advance the final state machine. Okay, so last thing about SDN. If you want, as I was saying at the beginning, an hands-on approach with SDN, well, the switches themselves are still costly. So if you want to buy now an open flow switch, that costs a lot of money still, because clearly we are not at mass market yet. But there are other solutions that are very extremely convenient. For example, to deal with these software switches. Okay, so what you do in this case is, of course, you don't have the physical device, but you have the application that runs on top of the controller, and that performs the network function that you want to implement. Then you don't have the physical device on which you have to install the rules, but you have everything else, basically. So you can do that. In particular, there is one that is called OpenV. V stands for virtual, OpenV switch, and it can be implemented on any virtual machine, for example. And then another interesting solution is the emulator. I don't know if you are familiar with Mininet. Mininet is used also for Wi-Fi, mobile networks, and it has been extended also to deal with open flow switches. So Mininet is an emulator that offers hosts, open flow switches, and also some controllers, or you can develop your own controller. And then what you can do is to download the virtual machine from this link on GitHub. You can follow the instructions and try to play with these things. So it might be nice if you do your own lab at home by following the instructions that you can find there. Okay. Okay, so we will stop here probably because it's already 10:30. So we will leave just the SDN application for cellular networks for later. It's just 3-4 slides, and then we will move to network function virtualization. I don't want to keep you too long. I know that it's Sunday, so let's have the break. Now, you know how the core network of LTE is. I guess you reviewed that also with Professor Casetti. So you know that we have a radio access network with E-node Bs, and then there is the core network that is called EPC. So we will use this acronym EPC to denote the core network of LTE. And inside the EPC, we have, for example, the mobility management entity, we have the serving gateway, we have the packet data gateway, then there are the database and the node that takes care of billing and so on. So there are several components here, but what we would like now to stress is what we can do through SDN in order to improve this setting. Because indeed what we have is that there are some nodes in the EPC that do a lot, right? Like the packet data gateway, the P gateway, is indeed very costly, as you can see here, because it does quality of service. Indeed, it handles the bearers, even if they are set up by the serving gateway. It also has some built-in functions, and then it is the gateway between the LTE core network and the internet, basically. So all data packets flow through this gateway. So it's a very, very important node of our architecture. And in our EPC, there is no clear separation between the control plane and the data plane. So as we said, some nodes like the packet gateway actually do both. Some functions related to the data plane and some function related to the control plane. So what we could do is to apply SDN to realize our EPC at a lower cost and in a more efficient manner. How? Well, by dividing, indeed, by decoupling the data plane and the control plane. So if you do that, you will have several nodes that are basically representing the data plane. They will deal with data packets. And then you will have one node that is the controller, so the packet gateway controller that instead implements only the control plane. So this might be more costly, but as we know, this software can actually run on any hardware. So it is, mainly software that can run on any hardware platform. And then we have these devices that at this point will be cheaper. So you may have many of them, and this means that even if you have a lot of traffic to deal with, well, you have several nodes to do that. You don't have problems of bottlenecks in your EPC. So that would be very important for scalability of our LTE core network. And in general, there are several other benefits that you can have by applying SDN to cellular networks. For example, load balancing. Right now, the traffic that is in excess, so when you have a lot of traffic to deal with, well, it is not clear how to deal with that in our EPC, because as we said, the nodes that are there are very costly. You do not have many of them available, so you try to have middle boxes that help you, but there is no efficient way to direct the excess traffic through these middle boxes. Why? Because indeed everything mixed, the architecture is a bit complex from the point of view of the protocols that are used, and therefore it is not extremely efficient. While instead, if we apply SDN, as we said, we may have several boxes that actually take care of the data plane, and then we have one controller that makes optimal decisions and can direct the excess traffic very efficiently through the data plane boxes. So that would be give the possibility to have a flexible routing of the traffic and also a better load balancing in the system. So that's one thing, but then we have also the possibility to monitor traffic very easily, because remember that according to our SDN principles, the tables that we have include rule, action, statistics. So the let's say the devices that realize the data plane will be able to actually measure the traffic and collect the statistics on all the packets that are processed, right? So that's very useful in cellular networks, because it means that you will be very easily have an idea of the amount of traffic that goes through every physical device. So even monitoring of the traffic and therefore billing functions that you implement at the controller will be easily realized. Third, vertical handover. Vertical handover means when user equipment, so our user, moves, for example, from the cellular coverage to the coverage of a Wi-Fi access point, and the traffic connection should therefore move from cellular into Wi-Fi, right? So this is called vertical handover because it's a handover between two different technologies. Nowadays, this vertical handover takes time. The procedure to perform that is not easy at all, and you may have packet losses. So if you think of a system that relies on SDN, well, then you will have exactly the same protocol, right? On the control plane, you'll have the SDN controller, no matter what you have on the data plane. So of the data plane, you may have, of course, the cellular traffic and Wi-Fi traffic that is dealt with different physical devices, but then the control is the same, right? It's the same for all of them. So at that point, moving the connection from one physical network to another physical network will be very easy because it will be done by the same controller. So this reduces time, that is good, and also avoids packet losses. So the performance can increase significantly. And then we can also manage the interference much better. Remember what Professor Casetti said probably in the first class. So we have the problem of interference between neighboring antennas, right? And what typically is done is to adopt solutions that are distributed, or let's say semi-distributed, meaning that you have a cluster of antennas and you manage the interference within this cluster of antennas, but then you have, again, border effects to account for. If you have SDN, well, then the controller will have a global view of the network so that it can make optimal decisions also related to the interference management. So it can assign radio resources to the different antennas in order to significantly mitigate the interference that you may have there. So SDN would be already very beneficial to the current cellular network architecture. But what our aim is actually to understand what it can do for 5G, right? So as we said at the beginning, this is indeed very important, and it will be very effective when combined with this second technology, that is the network function virtualization, NFV. So let's look at this second concept. Now that we understood what SDN is, probably NFV would be even easier to understand, because this is indeed the second key technology toward 5G, toward network slicing. So again, let's consider what we have today and why they have conceived this new paradigm that is network function virtualization. Now, the reality is that our mobile network operators, right, they provide network services. So they provide connectivity, in particular, of course, to mobile users, in being mobile network operators in this case. So the network services are typically a combination of single network functions. For example, if you have a packet, first of all, you have to inspect the packet. Then you should have a firewall that decides whether the packet should be dropped or allowed. And then you should have, for example, routing in order to route the packet, right? So connectivity, that is the network service in this case, can be thought as composed of three network functions: packet inspection, firewall, and routing. This is a simple example, but just to give an idea. Okay? So our telecommunication operator, in this case, has to provide the connectivity service. In order to do that, it has to have equipment that performs these three functions, right? So if you then consider mobile connectivity through 4G LTE, well, then the service mobile network connectivity will be composed of different functions. We know that there is the node B, and then you have the serving gateway, and then you have the packet data gateway, for example. Okay, so you can consider the mobile connectivity service as composed of these other three functions, and each of them, of course, is a network function. So this is fine. This is what we had so far, right? And in order to do that, as we said, since we do not have yet SDN applied to our networks on a large scale, our telecommunication operators, what they do is to buy these equipments, as we said before. So in the case of the connectivity service, they have a packet inspector, they have a firewall, and they have a router. In the case of the mobile connectivity service, they have a base station, an eNode B, they have the serving gateway, and they have another piece of equipment that is the packet gateway. So this is fine as far as the services are static. That means that they do not change, they do not evolve so frequently. Because if they do, then the telecommunication operator is clearly in trouble. Because if the service changes, it means that some of these network functions that compose the service will change. And if it will change, you will need to change the piece of equipment that implements that function. So if this changes frequently, you need to change all the equipment, and that's too much costly, right? So this is the motivation why our telecommunication operators have thought of a different paradigm, And basically, this new paradigm has led to the network function virtualization. On top of what we said, let me also stress that another good reason to change the current paradigm is the competition with the so-called over-the-top service providers. Over-the-top service providers may be Netflix, Dropbox, Google, and so on. Why? Well, because it is a fact that these guys are making a lot of money, right? While the telecommunication operators' revenues are decreasing year after year. So there is no way they can keep going on unless they change the way they operate and become competitive with these guys. So our telecommunication operators also need to, let's say, change a bit their role. They cannot provide static services. They need to provide services that are dynamic, that adapt to the new needs in a way that is cheap and fast. So able to evolve very quickly as the rest of the world does. So this is our motivation to move toward a paradigm like network function virtualizations that reduces the costs, allows for services that have a short lifetime, and to create a system that is extremely flexible. Now, the key components of this new paradigm of network function virtualization are virtualization, as the name says, and orchestration. So now we are going to explain what NFV is by introducing its main components, virtualization and orchestration. So let's start from virtualization. We know already something about it, right? Because while looking at SDN, we already said what virtualization is. Virtualization is the ability to create an abstraction of your resources. And it is performed by the SDN controller. So NFV actually takes the SDN word as a basis. NFV can exist because we have SDN. SDN does a great service to NFV. SDN decouples the data plane from the control plane. So now you have that the control plane is purely software. It can run on any data center that you like, even very far away from the physical devices, right? And remember the example that we gave, the SDN controller can provide an abstraction of the physical resources. The abstraction that you need to let your application run, right? And we had applications in the controller, right on the controller, that could exploit this abstract view of the resources, make decisions, and so on and so forth. So now the concept is very similar. Think of having SDN. The SDN controller produces this abstract view of the resources for you. You are a sort of application on top of the controller, but you are not in the SDN world. You are outside the SDN world. You use the abstraction provided by the SDN controller. And this is indeed what our NFV does. Okay? Sit on SDN and exploit the abstract view that SDN provides. Now, let's stick, however, to the virtualization concept for now. Yes, please. Right, so
another problem is in SDN the synchronization matters right now. Synchronization matters, and it is only time synchronization. And we know that every device
So,
The thing is, it is better to use the same vendor product in a particular area rather than different vendors. So SGA will open, it may open only few vendors.
yeah, so let me answer first the point that you raised at the beginning. So logically, we have only one controller, logically. But actually, in the practice, you may have several controllers, and you may also make your system resilient to failures by considering that controllers can actually, let's say that you have backup controllers, if you like. Okay. Remember that controllers, however, are software things that run on data centers. So you can have a high level of reliability in that. And so you have physically, you may have several different controllers, and controllers can also talk to each other. I didn't go into the details because we didn't have so much time, but actually there are solutions that allows you to develop a protocol for intercontroller communication. So the system and the architecture of the network can be a little bit more complex of what we said, and take care also of the issues of reliability, right? So from the point of view of synchronization, well, the control plane, it depends on what you have to do actually, but in general is much slower than the data plane. So the data plane needs to be very, very fast, while instead the control plane, the time scale at which the control plane works is much slower. You need to make decisions, for example, when some events occur. Then you have to make decisions quickly, right? Because if you have to recover a link failure and reroute the traffic, of course you have to act quickly. But the synchronization, let's say, among the controllers is not a difficult issue to address, okay? So talking about virtualization, in the following slides, we'll try just to get a better idea of this concept and provide an example that helps to better picture in your mind what this virtualization is, right? So the definition is here. It's an abstraction of the resources that allows you to retain the important information and to neglect the details. And what I would like also to put forward is that this abstraction can be done not just for network resources, as we have said so far, but also for computing and storage resources. So what we'll have is that a controller, an SDN controller for network resources, but you may also have an SDN controller for computing resources. So physically you have CPUs, right? CPU in your nodes, and the SDN controller for the computing resources. It will make an abstract view of your computing resources based on the CPU availability that you have at the different devices, physical devices. And then you have an SDN controller for storage resources. So we can stick to the networking, let's say, case, but the same concepts apply also for computing resources and for storage resources. So in the end, you will have an abstract view of the three of them that is available for NFV. Okay, so to better picture this virtualization concept, let's consider this example, because this is probably something that you can easily understand. You deal with that very often. So you have a laptop, for example. The laptop has got a CPU, it has got a memory, and then you can have a virtualization layer that basically creates a partition of your physical resources, so that a part of your CPU and part of your memory can be managed by, for example, for example, an operating system like Windows, or you may have a Linux partition, so another operating system that uses another fraction of your CPU and your memory, right? So this is an example of virtualization, because clearly you have some physical resources, but then through this virtualization layer, you are able like to slice these resources, and you provide an abstract view that is under the control, each of them is under the control of a different operating system, right? So this is something that can be done also for networks. So you have a network, you have your switches, so physical devices, and thanks to the SDN technology that we explained before, you can actually have an abstract view of your resources. You can also partition these physical resources into different slices, and then each slice can be managed by a different entity. So in particular, just to give you a practical example of this case, there is the Flowbased SDN controller. The Flowbased is an SDN controller, but it's actually a proxy. So what it does is to interact with the physical devices, with the switches. And then it creates an abstraction, so virtualization of these switches, creating different slices. And you can create these slices by, for example, based on the switch ports, so at layer 1, or exploiting the Ethernet address, so layer 2, or exploiting the IP addresses, so layer 3, and so on. So you can create these slices that are characterized by, for example, the IP addresses of your routers. And then, once you have these slices that are created by your SDN controller Flowbased, well, these slices can be managed by different, each of them can be managed by a different controller at a higher layer. So each of these are still OpenFlow controller, but each of them will take care of one slice that has been created by this proxy SDN controller. Okay, so the concept is very, very similar to the one that we explained in this slide. So virtualization is basically about providing this abstract view, this sort of abstract view of your physical resources. Okay, so now that we understood this concept of virtualization, let's go back to NFV, and in particular, let's introduce this very important definition for the NFV technology, that is virtual network functions. So what NFV does, first of all, is to take as input the virtualization, the abstract view provided by the SDN controller, and consider this abstract view of the resources and implement on these resources network functions in software. So basically, in simple words, in this case, it's exactly the same thing that a controller application would do in SDN, right? Because also in SDN, we had the physical resources, then the controller was providing this abstraction, and then we had the applications on top of the controller that were using this abstraction to make decisions and perform, for example, routing. We had the example with the Dijkstra algorithm, right? That performs routing. Routing is a network function. It was implemented in software, so it was virtual because implemented in software, and used the abstraction provided by the SDN controller. So now, from that point of view, we have exactly the same thing, but the network function, that is still virtual, is software, is implemented out of the SDN world. Okay? And it's called virtual network function because indeed is software. Okay? It's not routine implemented in hardware, it's software. And as we said, it is made possible thanks to SDN. SDN creates this controller in the data center. So we create extra software in the same data center on top of SDN, and we realize the network functions that we like. So V and F are virtual network functions, but NFV does something more than that, because otherwise you could say, well, we could have the SDN applications that were fine too. Why do we need this new concept? It's not that new. It's just that you move these functions a bit, above, but it's exactly the same thing as before. Well, there are two main differences here. One, sticking to virtual network functions, is that NFV not just implements these virtual functions, but also compose them together in order to provide a service. So the network service that we were talking before, now it becomes a virtual network service. So the packet inspection, firewall, and routing, now these three are virtual functions that NFV can realize and connect together, so that altogether you have a virtual network service that you can create. And if you think about it, well, this means that given the virtual network functions, you can combine them as you like through NFV. So you can have the MME of LTE, you can have the serving gateway, packet gateway, you can have a packet inspector, you can have a firewall. Well, you can combine them together and create new network functions. So it's like pieces of a jigsaw puzzle that you can put together and obtain the puzzle that you like. So that's what basically NFV does. Thanks to SDN, but it has got this different flavor with respect to what SDN can do. Okay? So in a nutshell, NFV decouples the physical network equipment that we're performing, packet inspection, firewall, routing, whatever, and it decouples that from the function, from the actual function that they realize. So now you separate, again, the physical devices and the functions that you want to implement. They are completely decoupled. And what you do with NFV is work in a virtualized environment. You are on top of the controller, so everything there is software, and you only work with abstract view of the resources. Okay? So this is a graphical representation of what we said. Very simple, like the packet inspection, firewall, and routing. So you can combine the three of them in a simple chain, linear way, like this one. But in general, you can have more complicated graphs. So each node of the graph is VNF, for example, and you can combine them as you like. Here is a representation of the EPC of LTE. So if you apply NFV, what you have got now is a virtual EPC, so a VEPC. Virtual because any of the nodes that were composing the EPC, so this is basically the mobile service. Here you have the E node B and then you have the core, but altogether it's the mobile connectivity service, can be implemented through NFV, And at this point, you will have actually a virtual eNode B, and then you have a virtual serving gateway, virtual packet gateway, virtual MME, and they are software functions that reside in data centers. Okay? Then you don't need the physical equipment to directly implement the software. The software can be in a data center. The other important aspect on FFV with respect to SDN is that the pieces that we consider, so the virtual network functions, are not the only one you can play with. Actually, you can now consider any application as a piece of your puzzle. Because remember, we are dealing with software things, software pieces, right? So the piece that you realize, it can be a routine firewall in software, but it can be any other kind of application, not necessarily a network function. So what we have is VNF, virtual network functions, but also virtual applications. And they are all pieces there that you can combine together to obtain a service. So for concreteness, let me give you an example that relates to the automotive world. So let's consider that your car manufacturer wants to provide as a service to its own vehicles the intersection collision avoidance service, where collision here is not between packets, okay? It's between vehicles. So you want to deploy this service at an intersection and provide this service to your vehicle so that they avoid colliding, so they avoid car accidents at the intersection. This actually is under study within this European project. It's an H2020 project called 5G Transformer, and we are part of this project. And there is also FCA, that is the well-known car manufacturer that has been conceived out of Fiat and Chrysler. They merged, and we now have FCA. So anyway, this is the picture that is, given the intersection, we want that the vehicle of a car manufacturer will have the client of this application, that is the intersection collision avoidance. And we know that thanks to, for example, 802.11p wave, our vehicles will broadcast periodically the CAM message. So remember what we said 2 days ago. We have periodic messages that are sent by our vehicles. They include position, speed, heading, acceleration, this basic information about the vehicle's movement. So they send these messages. These messages could be also received by your eNode B. Okay? They are received by other vehicles, but if you have the proper radio interface, they could be received also by the eNode B. So here we have the mobile communication service through, for example, LTE. So virtual eNode B, because we have virtualized that function. And then we have the virtual EPC, because again, the EPC is realized through virtualization. So then the EPC has got the packet gateway inside that will be able to send the packet, the information included in the CAM, toward a database. So we are collecting all CAMs that we receive from the vehicles in a database. This database, you can think of it as managed by a third party that is trusted by all car manufacturers, right? So here you collect the CAMs sent by FCA vehicles, BMW vehicles, Toyota vehicles, and so on. Then our car manufacturer can access this database and get this information that was included in the CAMs. And it can use this information for different services. one of them is indeed the intersection collision avoidance service. That means that here we'll have an algorithm that takes the position, speed, acceleration, heading of the vehicles at the intersection and computes the probability that two of these vehicles will collide. Okay? So if there is a pair of vehicles that are likely to collide, then our algorithm will give it as an output. And at this point, we can create a notification message, the DNM message that we talked about 2 days ago, and send this notification message again through the mobile communication service that will send this message to the vehicles so that they will be notified about the risk of a collision at the intersection. And then clearly the vehicle can exploit this information and basically through the actuator, for example, activate braking at the car, right? So there are many other services that the car manufacturer may want to provide. For example, he may want also to access this information collected through the cam to come up with a profiling of your drivers. So considering they are human drivers, well, you may want to have a profile for each of them, derive statistics that tells you, the risk of car accidents under certain conditions, and so on. So you may actually use this information for many other different services. So this is the service that the car manufacturer wants to provide. So it will tell you, well, I want to have this service. Now it's your job to deploy the service and support the service through the network. So the first thing that you can do through NFV is to translate this service representation into a graph. A graph where the nodes are either virtual applications or virtual network functions, right? Because, for example, the communication service, the mobile communication service, is actually a network service composed of different virtual network functions: virtual inode B, virtual service gateway, virtual packet gateway, right? So here we have virtual network functions, while the intersection collision avoidance algorithm is a virtual application because it does not do anything from the networking point of view. It's an algorithm that takes information in input and gives you as output the probability of vehicle collision. So it's not related to networking, but this is an application that can be realized in software. So that would be a virtual application, okay? And this will be the database that you have to implement to collect the information received to the CAM. Here is the message encoder and so on. So basically, given that the vertical, in this case the car manufacturer, gives you a service through NFV, you can translate this service request into a graph composed of VNF and virtual applications. And then what you have to do is clearly to actually implement the single virtual network functions and the single virtual applications using what? Using the abstract view of the resources that you get from the SDN controller. Okay? So this is an example of how you can combine VNF and VA to obtain a service. So let's now look at the second piece of NFV, that is orchestration. Because now we know what virtualization is, let's look at the orchestration. So let's explain what orchestration is through this picture. So this is the architecture that actually includes orchestration and also tells you and summarizes how SDN and FV can be combined. So this picture actually allows us to explain what orchestration is, and at the same time gives you a global view of whatever we said so far this morning. Okay? So let's start from the top of the picture, that is the vertical. So the vertical, for example, car manufacturer, is the one that gives you the service specifications, right? Like the intersection collision avoidance service, what it should do, what it should be. So now you have the specifications from the vertical. You can skip this one, it's actually a detail. And what the orchestrator does, that is this block here, well, is to get the specification provided by the vertical and compose the corresponding graph, the one that we saw in the previous slide. So you need someone or something that translates the vertical requirements into a graph of VNF and VA, okay, virtual applications and virtual network functions. Now, these virtual applications and virtual network functions that connected together realize your service need to be implemented. How can you implement them? Well, for the virtual applications, you just need some virtual machines, right, somewhere. And for the virtual network functions, again, you need to implement them in software. So clearly you will use containers, virtual machines, whatever. But remember that we have got this graph to realize. So if you realize, for example, the intersection collision avoidance algorithm in a virtual machine, and you have the database somewhere else, then you need to connect them, right? Or if you have the virtual EPC that is implemented in another virtual machine, then you need to make sure that actually these two communicate. So when you implement your virtual applications or your virtual network functions using virtual machines, then you have to make sure that the virtual machines can talk together according to the edges of your graph. Okay? So this orchestrator not just has to translate the vertical request into the graph, understand which VNF or VA you need, but then you need also to implement this in software into virtual machines that are in some way connected with each other. And in order to implement these virtual applications and virtual network functions, therefore, you have to look at the resources that you have, select the virtual machines, make sure that you have virtual links that connect them. Okay? So what you do is to look at the abstraction of the physical resources that the SDN controller provides, and use this abstraction in order to place your functions, virtual functions and virtual applications properly on this abstracted view. The pool of virtual resources, so the abstract view of the resources that the SDN controller provides, plus some other physical resources that you may have to manage that are not under any SDN controller, compose the so-called NFV infrastructure. So the NFV infrastructure is the basis on which you have to deploy the VNF and the VA. So the NFV infrastructure is composed of physical resources and virtual resources, where the virtual resources are the abstraction provided by the SDN controller. So in order to do all that, as we said, we need an orchestrator, we need a brain, we need some intelligence that tells you how to perform each of these steps. So move from the service to the service graph, decide where to implement the VNF and the VA, considering the resources that you have available. So this brain is the orchestrator. Okay? Now, the orchestrator has someone that helps him. And this someone is the VNF VA manager and the virtual infrastructure manager. What do they do? Well, the virtual infrastructure manager is the one that instantiates, for example, virtual machines when you need more virtual machines to deploy your VNF or VA. So it's the one that manages this NFV infrastructure, creates virtual machines, removes virtual machines, so it determines also the life cycle of the virtual machines. The VNF VA manager, instead, is the one that actually deploy, based on the instructions of the orchestrator, deploys the VNF and the VA on the NFV infrastructure, so on the virtual machines, and determines the life cycle of these functions and applications. Okay? But the brain, as I was saying, is this orchestrator here. So basically that's it. We now have the combination of SDN and NFV. Any question on this part? Is it clear to you? Okay, so the concept is a bit difficult, I think, to acquire because everything becomes software, everything becomes virtual. But this is indeed the new concepts that we have there. So it takes some time, you know, to think about and figure out how everything works. So in the slides, in the following slides, you have reported what I explained to you looking at the picture. So we can now move back to network slicing, that is using SDN and FV for 5G. Okay, so we need to close the circle with that. So network slicing is indeed our goal, right? To slice the network. So let's now see how we can use SDN and FV to achieve the goal that we stated at the very beginning. And here is the slide that basically summarizes everything and explains how to perform these network slices. So let me start from the top again. At the top, we have the services that are requested by the vertical. So let's consider again the intersection collision avoidance as an example. Whenever the vertical, that is the car manufacturer, tells you, I want to deploy this collision avoidance service at this intersection, well then, that's a service instance, right? A service instance because you want to deploy that service at that specific intersection. So it's an instance of your intersection collision avoidance service. So through the architecture that we saw before, so through the NFV orchestrator, as we said, we are going to translate the service into a graph, right? And then the orchestrator, what the orchestrator does is to deploy the graph. That means deploy the VNF and the VA in software using virtual machines that realize, that implement what you want. So the set of resources that are used to deploy the VNF and the VA of the graph is a network slice. So you can think of a network slice as the graph that represents the service and the associated resources that you use in order to implement the functions and the applications that compose the service subgraph. Okay, that's a slice. And as represented here, each slice may actually include sub-slices. What do I mean by that? Let me go back with our slides. Here, this was the graph that we had before. So if you consider this graph plus the resources that you use to realize it, well, that's a network slice. But if you focus on this piece of the graph, well, this piece of the graph is per se a subgraph, right? Because inside we have the virtual inode B, we have the virtual serving gateway, we have the virtual packet gateway. So this is a sub-slice because it's a subgraph. So considering the resources that you use to realize that, that will be a sub-slice that you use to build this more, wider, larger graph. Okay. So what this picture here represents is indeed this concept that given a network slice, this can be actually composed of different subgraphs that are sub-slices per se. And clearly, as we said, the slices, sub-slices use resources to deploy the VNF, the VA. So here you have the representation of the resources that you can use in order to deploy your slices and sub-slices. Okay. So you can have here some, let's say, more formal definition of a network slice, but the meaning is what I explained to you. The only thing that I would like to stress is that when you deploy your service graph and you look for resources to implement your virtual applications and your virtual network functions, you have to configure your resources in such a way that the quality of service requirements, the KPI that we introduced at the beginning, are met. So you cannot just select any virtual machine to implement your intersection collision avoidance algorithm. You have to select a virtual machine that ensures you that a certain number of instructions are performed per second, that is sufficiently basically fast. Or when you have your database that collects the CAM information, well, you have to assure that it is large enough to include all the CAMs that are sent by the vehicles at that intersection. So if you expect a certain vehicle density there, you have to dimension, of course, the database accordingly. And therefore, you have to look some storage that is suitable for your service. So it's not just to deploy your functions and applications on resources, but you have to allocate the resources properly. And this becomes even more challenging when you have the sub-slices that are shared, used by different services. So for example, the virtual EPC can be used for the intersection collision avoidance service, but it can also be used for video streaming. That is another service, right? Well, at that point, the same resources will have to meet the requirements of the two different services. So it's like scheduling, a scheduling problem, where you have common resources, in that case, that is the sub-graph, the sub-slice that realizes the mobile communication service. So that's the common resource that is used by different users. And in this case, your users will be the different services that rely on the same sub-slice. So at that point, you have to solve clearly a scheduling problem. So here you have basically reported in the slides for your record what we discussed. And here we have a set of references referring to NFV. These are standard documents by the European Telecommunication Standardization Institute, ECE, and there you will find all the details on how your NFV architecture should be defined, and how the different pieces of the architecture interact. The last few slides that I would like to explain about this network slicing and 5G is, let me actually skip these definitions, but let me focus on this picture. It's a bit small, I hope you can see that. So this comes again from this 5G transformer project, and basically summarizes the vision of the 5G core network based on what we said. So here at the top you have the verticals, and actually in general you may have verticals as car manufacturer, content provider, and so on. But the more general term that we should use is tenant. Tenant is whoever wants to use the network below in order to provide a service. So tenant is a bit more general than vertical. Tenant could be the mobile operator itself. Now, they, as we said, provide the scheme, basically, of the service that you should implement. So basically the graph that we need to implement. And then, as we said, the orchestrator of our NFV architecture will have to deploy these graphs by using the resources that are available. And this means that given certain physical resources here at the bottom, we'll have the SDN controller that abstract these physical resources, and the orchestrator will use this abstract view of the physical resources to use some of them to implement the different services. So here we have these slices that we were talking about. The different slices rely on the same physical resources, but as we said, through the SDN controller, you can slice the physical resources and use each slice to support different VNF, different VA, that means different services. Okay, so this will be the service, for example, realized through this slice that is related to entertainment. This slice will be instead for the automotive service. This slice will be for the e-health service. And all of them rely on the same physical infrastructure. Let me skip that because it's a bit too detailed, and I think that we are almost done. So let me just jump to the multi-access edge computing, because this is an important concept that I would like to introduce very, very quickly. So multi-access edge computing, MAC for short, is actually similar to fog computing. So you may find both terminologies, they refer more or less to the same idea. What is this idea? Well, remember, we said, thanks to SDN, we have that the control part can be anywhere. We said any data center, but it can be anywhere. And then we said NFV builds on top of that, right? Everything now is virtualized, and NFV works on top of the SDN controller. So again, in a virtualized world, in a software world. The idea of MAC is very simple. What it says is that let's not use for the SDN controller and the NFV data centers that are in the cloud, that are far away from our end users, but let's use resources that are at the edge of the infrastructure, close to our end users. Why? Well, because if you have your SDN controller and NFV architecture that works at the edge of the network, think of our current access points, of our current base stations, right? They have CPU, memory. We can equip them with enough CPU, with enough memory and storage, so that we can have the SDN controller and the functions, virtual applications, and so on. So the necessary virtual machines at the access point, at the base station. Well, at that point, we'll have that the delay, the latency related to our service will be very much reduced, because everything is close to the mobile end user. So in the case of intersection collision avoidance, for example, the service is for vehicles. And if you remember the KPIs that we had at the beginning, they were very few milliseconds. So we are talking about 3 milliseconds, remember, about for the automotive, in particular, the autonomous vehicles. So how can you achieve a 3 millisecond latency? That's very, very short. So clearly you need a radio link that is extremely efficient, but also you need that your server, your application is right there. It cannot be far away in the cloud, because that would mean that you have to go back to the server, there you have your algorithms, and then come back. That would take too much time. So the concept here is very simple. It's just that to have, since everything is software, why do you need a data center in the cloud? If you put enough CPU and memory at the edge, well, then you can build your virtual machines, applications, and so on, everything there, right? So this is the idea, this is the concept that is basically represented also in this picture. So just move whatever was in the cloud closer, and that's why I said that this Mac concept is very close to fog computing, because the idea is to move everything from the cloud to the fog, so closer than the cloud, right? Closer to the ground where the users are. What are the benefits? Well, as I said, very low latency, ultra low latency. But there are others. Think of the Internet of Things applications, where you have sensors that generate lots of data. Why do you need to transfer all this data to a server that is in the cloud? You will consume a lot of bandwidth. It's much more efficient to process the data locally at the edge of the network, and so you will save a lot of bandwidth. And clearly, you will save also energy, right? Then you have better privacy, because now your data are kept locally, that is closer to the user, and they are not moved to data centers and storage that is in the cloud, managed by third parties and used, well, how you don't exactly know, right? Also, there is higher resilience, because you have the possibility to replicate your servers at several different locations, instead of having, as your colleague was saying, just few points of possible failure in the cloud. So you can have everything at the edge, smaller, but many instances of that. And clearly you have the possibility to develop services very, very quickly. There are some cons. The availability. So if you need very high availability, it means that you have to replicate these services everywhere. So from that point of view, that might be a challenge. Also because if you have to maintain consistencies in the data that are stored at these different locations, while maintaining consistencies, it may result in quite a high overhead. So that may be a problem. And the fact that since your users move, right, so that's a mobile network, well, if you deploy your service, let's say at the edge of the network, let's say at an access point, when your user moves, you need to migrate the service instance to the next access point in order to follow the user. So that may, of course, end up in a higher complexity in the system. So we are basically done. This is just an example actually taken from the work done at IIT in Taiwan, where they are using this MAC concept, for computing concept, for the detection of parking spaces or for detect illegal parking. So the fog computing, or MAC as you want to call it, allows you to develop services that are also that are targeting a smart city environment. So most of them are targeted for more sustainable environment from the transportation point of view, but also for smart city in general, so pollution control, energy consumption reduction, etc. Just to conclude, I would like to say that we have covered some topics, but clearly the innovations that we have and the novelties that we have in this field are many. So, for example, we didn't touch at all the IoT, Internet of Things standards that are out there. They are also very interesting and maybe relevant. So if you are interested, I solicit reading of the specifications for IoT that has been issued by 3GPP. That's in particular something interesting. And also the application of the concept of MAC, or for computing, to IoT. So with that, we are done. Thank you so much for your attention. And if you have any questions, of course, please feel free to ask. Any question or anything that you'd like to